That is for this sequence of instruction. Okay, so let's look at this example again. Right, we just talk about the sequence. Right, without forwarding, we need to insert quite a few bubbles or quite a few no-ops. Right, and these are the registers where we have to, we have this data dependency of data hazard issue, and with forwarding, okay, really nothing, right? So all these data hazards are resolved. Okay, all these R-type instructions are fine, which is really cool. Means that it really means that we can push this instruction one by one, okay, and they will flow through the pipeline without any hiccup. Okay, let's look at the different sequence. What about this one? Load. Okay. This is load word, LW. Okay. And OR and sub. Last time I talked about the Gantt chart. Right? There's a way to quickly write down the schedule of the pipeline. Right? We also come up with a shorter acronym for the instruction. There's a different pipeline stages. LW, the load word, we can start with fetch, right? And then decode, then execute, mem, and write back, right? Next cycle, same thing, right? Next instruction, I mean, same thing, right? And the third instruction, same thing. Okay, so let's look at, do we have a header or not? First, without forwarding, do we have header? Yes, right? We need to worry about this R1 for OR, and okay, then this one's fine. Let me hide that animation. This one's fine, right? With forwarding. Without forwarding, this R1 is also a problem. With the forwarding that we just saw, this one's fine, right? Because we can forward from OR to sub. But how about this one? This R1, right? Why is this still a problem? Where do we get R1 for load, for LW? In CC 1, 2, 3, 4, 5, 6, 7. Which cycle? CC 5, right? So when we write back, but when's the earliest? What is the earliest point? Okay. Of course, if there's no forwarding for load, then we're going to talk about forwarding for load, right? So of course, there's an issue. We write back, right, to reservoir in W, in the write back stage. But when's the earliest point where we can get R1? Right at the end of 4, maybe, right? Okay, so basically this point. Okay. Let me just draw a line. So later on, when you guys try to detect whether there's still a header or not with forwarding, whether a forwarding can resolve a header or not, first identify which stage is producing that value, right? For load, the mem stage, not EX stage, right? The mem stage is producing the R1. It's later, one cycle later than EX, right? Then we just draw a line, okay, like this. Then we just look at where do we need to consume that value for OR, where do we have to consume that value? Also here, right? X. And this is to the left of the line, meaning that we actually have a problem with forwarding. Okay, we cannot forward. Even forwarding may not help. But how about this guy? How about subtraction? This guy. Subtraction. Can we forward? From load to sub? Yes, right? Because for subtraction, we use R1 here, which is to the right of this line. That means there's this possibility to enable the forwarding. Okay. Of course, if all of this, right, are just R type, right, just and or at sub, right? So those are fine. Forwarding can solve because all the results are produced at EX stage, and all of them are used in EX stage, right? So that's where we can always forward. But this is a different scenario where the result is produced at the memory stage, and for this one we cannot forward anymore. Okay, but let's build the path, right? For this one first, we do want to resolve some hazards, right? As many as possible. So let's look at, this is without forwarding, right? The data hazard caused by load. This is a longer sequence. We have R1 produced over here. If you don't do any forwarding, you write it right back here. Then of course, right, we have these red lines where we cannot really, get the updated R1. Okay. So let's try to do some forwarding. We just agreed that we can forward for this guy, right? R1. How do we do the forwarding? Tell me which cycle to be forward. Let's focus on sub first. Cycle 5, very good, right? Tell me the name of the forwarding path. It's something to EX, right? Very good. WB to EX. Okay. This is the forwarding path. Okay. How about this guy? Okay, this clear, right? We can, this forwarding is pretty straightforward. How about this guy? How do you forward for this R1? We can also forward, right? Since we can forward for sub, obviously we can forward for end. How do we do this? Tell me the path. It's got to be WB, right? The source. WB to first, when we do forwarding, right? It's really happening in the same cycle, right? That's just actually all we need to do is to focus on the cycle. Okay. And the only chance we have is this. Right? Just like what we discussed with the bonus question. We need to overwrite the value being written, right, in front of the ID/EX register. We are basically doing a WB to ID forwarding. Okay, so this is the things that we can resolve, right? And this guy is pretty much hopeless, right? Because if you directly do this, someone may propose that why don't we just do this, right? Why don't we just directly send the result of the load to the input of the ALU? If you do this, what is the problem? So we are collapsing. We are really collapsing. Right? We are fusing two pipeline stages. Right? We are actually collapsing them. We're actually not doing pipelining anymore. Right? So basically, this whole thing is combinational. Is it clear? That's not something that we want to do. We do want to achieve a higher clock period. We do want to divide it into a few pipeline stages. Okay, so then we have to do something about this, right? We cannot go back in time, like Alma said, right? We cannot forward from CC5 to CC4. Okay, this is not something that we can do. So we have to do something about this. Again, dumb solution, let compiler do the work, right? How about we just insert no-op? Okay, this helps, right? At least functionally, this is correct. Then we can do the forwarding, right? After inserting just one no-op, we can do the forwarding from the load, right, over here. Okay, load to the OR instruction. Just one no-op is sufficient. Okay, and then the other forwarding will just work, right? There's another forwarding. And we can do the same, right? In hardware, we can detect the hazard and then insert the bubbles on the fly. This is pretty much the same, right? Very much similar to the compiler-based approach. Okay, and there's actually something that's more interesting. This is actually a hardware software co-design solution. This is where we actually define something new in the ISA. What is the ISA again? You guys still remember ISA or ISA? Very good. Good. Instruction set architecture. This is the contract. Right? Remember, this is a very important abstraction. This basically is the abstraction for the microprocessor. This is a contract between the hardware, the microprocessor, and the system software, like compiler and like operating system OS. I'm going to be talking about OS a little bit later on. Okay. This is where we can actually introduce something called delay slot. I'm going to make it very concrete pretty soon, but let me just expand the animation. So this delay slot is defined in ECE. What we are doing here is that for this kind of load instruction, we will just say that whatever follows this load instruction is always going to be executed. The hardware doesn't need to care. And whatever follows this instruction, follow this load instruction, is going to be safe. Okay. And the slot right after the load is called a delay slot. Again, this is fairly abstract, but if I give you one example, right? Again, we have a load, right? With the delay slot in the ISA. Okay? In the ISA basically says that with a load instruction in our 2300 ISA, okay, we will just assume that, okay, the hardware will just assume that whatever follows the load is always going to be unconditionally executed, and it's not going to cause any harm. Okay. This is the so-called delay slot. Okay. Basically, we always have something. We have something in the right after the load. This is a slot called a delay slot. But of course, this sounds kind of counterintuitive, right? You know, what if there's a dependency, right, between load and add? So this is where the compiler needs to step in. The compiler, if the compiler sees the dependency, right, if add is indeed dependent on this LW, then we need to insert the NOP. Okay. We need to insert NOP. Otherwise, we can find something that's independent from LW, the load. We put it in the delay slot. And the hardware is not going to check. Okay. The hardware will just assume that there's no data hazard between these two. That's why I'm calling this a co-design solution. Basically, both hardware and software, they need to agree on the same assumption. This assumption is called the delay slot. Okay. Yeah, Amanda, right. So this is sort of like it's very much like a bubble, right? It's really that if you can find something useful to insert in this delay slot, right, then we are not wasting a cycle in hardware. Otherwise, if you cannot find anything useful, then we have a bubble, basically. Okay, so let me make it again a lot more concrete. So this is where the compiler, right, needs to be hard at work. The compiler needs to find instructions which are independent, okay, from the load, and then insert it in the delay slot. Okay, so let's look at the trivial case. One trivial case is, the compiler can always choose to insert NOP in the delay slot, right? But the nice thing about the delay slot is it doesn't have to be a NOP. Okay, this is a delay slot. Okay, if we look at this sequence, guys, is there an instruction that we can move? Is there an instruction that the compiler can move to replace the NOP? Just look at the sequence. Very good, right? If you label this, right? 1, 2, 3, 4, 5, 6, right? If you look at instruction 3, can we move? No, right? Because or instruction 3 or depends on load. We cannot move it to the delay slot. Same for 4, right? Also depends on load. Same for 5. But instruction 6, this guy, okay, is independent, right? It's also independent from the previous instruction, right? It's not dependent on or, stop, and end. Also not dependent on load. That's where the compiler can make this move. The compiler will just put it right behind load, and the hardware is not going to check, because the hardware is going to assume that the compiler has already guaranteed the correctness, right? When it does this kind of the code transformation for the delay slot. erase this in case my drawing is not clear enough. Right? I'm using this arrow to indicate the move. Right? And we replace it. Okay. Is it clear? Right. So in Lab4, you guys are not going to be worried about the compiler. Right. So we'll give you you guys will only build hardware. Okay. Don't worry about this. You don't need to implement another compiler optimization path. Let's look at another example over here. Is there anything that we can move? Can we move add-I? Yes or no? No, right? Not this one. Okay, because if we move add-I, we are not gonna get the correct R6, right? Because there's a dependency between and add-I. If we move add-I, we are not gonna have the correct program anymore. Okay, so in this case, we have to be less greedy, right? The compiler has to be less greedy. The compiler will stay put and just put the no over here, which is fine, right? We always want to get the correct program, even though it's a less performant. Okay, any more questions about delay start for load? Okay. All right, so let's move on. Let's talk about branches. We talked about branches at the end of the last lecture, right? But we really haven't talked about the implication of branches in terms of the data hazards. If we think of branches, we also need to consume some source operands, right? This is something that we are going to discuss in the next lecture, the data hazards for branches. And for today, let's focus more on the things that we did not touch on last time, right? Last time, remember that I did ask you guys, right? If you look at the microprocessor, we are making the branch over here. Somehow my pen is not working anymore. Maybe it's out of battery. It's fine. Okay. Let's just follow my laser pointer. Okay. If you look at the branches, right? Remember, we are making the decision here in the stage EX stage. We update the PC in stage EX because we are saying that we need ALU, right, to compute in some cases whether this is 0 or non-zero. We need this output flags, these output signals to drive the CU. CU is a control unit where we can make a decision, right, whether we are taking the branch or not. I already asked you guys a question, right? Is it a problem? Many of you are already saying yes, right? Because if we are making a decision here, we will already have instructions. We have already fetched 2 more instructions into the pipeline, which might be an issue, right? Okay, so let's see how we can handle this. Okay, if the question, if this problem is still not too clear, here's a more concrete example. We're doing BQ, branch equal, which means that if R2 is the same as R3, we take the branch. We go to this target address, right? We go to this target instruction labeled by X. Otherwise, if the branch is not taken, we are going to execute OR and sub. Okay. All right. So think about this pipeline that I just showed you. If indeed we are taking the branch in this clock cycle, right, in this stage, it's going to be too late, right? We will be fetching OR and sub into the pipeline, and if the branch right, if this branch condition ends up to be true, then we are in trouble, right? We need to somehow get rid of these 2 instructions. Otherwise, the whole pipeline execution is just wrong. This is something that's called control hazard, right? This is a different kind of hazard. We have been mainly focused on data hazard. but the branches, right, this kind of control flow may also cause another kind of hazard, control hazard. So this is basically what I just described. What we really want to see is, right, we if the branch is taken, we execute this instruction, right? This is the next instruction. Otherwise, we execute these two, right? We don't really want to have a scenario where the branch is actually taken, but somehow we also execute the OR and sub instruction. This is basically the concept of control hazard. Hopefully the concept is clear enough, right? Simple enough. But what can we do about this? Right? Is there anything that we can make it? We can make the pipelining, the hardware, right? We can make its life simpler. First thing we can do is we can try to reduce the branch delay, right? So right now we have to wait until the third stage, the EX stage, to make the branching decision, which is too late. We already agree on. But can we make the decision in the first stage, in the fetch stage? Is it possible? Yes or no? Then fetch instruction, can we make any decisions? No, right? Why not? Because we don't even know whether that's a branch or not, right? We don't even have the decoding. We haven't decoded the instruction yet. We just fetch this 16 bits, right, in our case, from the instruction memory, and that's it. That's too late, right? Sorry, that's too early. That's too early. And we already agreed that EX is probably too late. So why don't we just do it in the second stage, in the ID stage? Because there, we already have the decoded instructions. We already have the registers, right? The IDs of the registers. We already know the type of instruction. We also have the values of the registers. We're already reading from the register file, right, in the ID stage. So the ID stage is actually more hopeful. So let's see how this can be done. In the ID stage, again, we are decoding the instructions, and these blue lines means the control signals. We will have the addresses of the source, right, SA register and source B, SB register, and we will have the values of these registers. Right? And that's where, let's say we are doing a BEQ. Again, my pen is not working anymore. BEQ. We already know, right? We can already make a comparison. So why don't we just allocate a comparator over here? Let's just introduce some additional logic. We don't have to introduce a full-featured ALU. Agree? Maybe let's just do let's just introduce a comparator like this. This is a symbol for comparator where we are just checking the equality or inequality. With this, we can drag the control unit, right, to make the branching prediction. Clear? Okay, see, these are the instructions that we want to support, right? We want to support the 2300 instruction set, we want to support BQ, B, and E. So that's where we are making a comparison using this box. But why do we drag out the sign bit? Why do we drag out MSB from this line, from this black line? What's the use of this sign bit over here? Very good. Okay, because we also want to support these two instructions, right? The BGEZ, right, and LT, BLTZ. So this is where we are checking whether RS, right, RS basic data A is right, no less than 0 or less than 0. That's where I just drag out the sign bit. Okay, I hope that you guys all agree that this is something that can be done, right? We can do it in the ID stage. That means we reduce a bunch delay by 1 cycle, which is great. But we still have 1 cycle, right? We still have this 1 cycle delay. What do we do? What's our next, right? So what is the solution? How do we handle this 1 cycle delay? We actually already talked about that for load. Any proposals? Any ideas? Now that we have a branching delay, right? Very good, Katie. Why don't we just introduce another delay slot, right, in the ISA. Okay, but this one is for a different kind of instruction, right? This is for handling the control hazard, not the data hazard. But the essence is the same, right? It's the fundamental idea is the same. So really, we want to make a contract, right? We want to add additional specification in the ISA so that the hardware know that when we are running a branch instruction, the one that immediately follow the branch is going to be harmless. That one's harmless. It's always going to be executed unconditionally. This is where we introduce the notion of branch delay slot. Right? In this delay slot, it can be a useful instruction or a no-op if you cannot find one. So that's basically the same idea, right? Behind the load delay slot. Okay, so let's see whether we can find one or not. Actually, there'll be a quiz as well, okay, after this example. So make sure that you guys ask questions. You're still not too familiar, not too comfortable with the notion of branch delay slot. But let's look at this example first. Okay, so this is the branch, right? BQ, and by default, compiler will introduce the no-op in the delay slot. Right, this is the safest way. But the question is, can we do better? Is there an instruction that we can move to this delay slot? Just want to make sure that you guys are clear, right? If the branch is taken, we jump to X. We jump to this, right? This instruction, and then we do AND and add I. Otherwise we do OR, sub, and add I. So basically, add I is always executed, right? Regardless whether the branch is taken or not taken. So basically, you guys are right. We can just move add I to the delay slot. Is it clear? Okay, but why don't we? Here's the question. So why don't we move X? Why don't we move AND into the branch delay slot? It's also gonna be executed regardless of the branching decision, right? This guy. What's wrong? First, we all agree that add I, right, is a good one to move. But what's wrong with AND? Wouldn't it change the address? Yeah, very good, right? So it may change but remember, this is done by the compiler, right? Compiler is going to generate the instruction. The compiler will calculate the offset. If you move it, then the compiler will change the offset, the immediate value, right, in that instruction. It will make everything execute. Yes, excellent point, Amanda. Okay, again, what I'm proposing is we move. Too bad that my pen is not working, and it's going to be moved here, right? So you guys have to imagine what's going on. So then what's going on here is that we do the branch, right? Okay, this really does not matter, right? Because we branch for X, we do BQ, and then we execute AND. Then there's no, regardless whether we do the branch or not, we're going to execute the next instruction, right? There's no more branches. OR and sub will be also executed unconditionally, which is bad, right? So we cannot move the branch target, but instead, so this guy can be moved. All right, okay, so this is what we just did. Okay, one last thing before the quiz. Last time I also talked about this PC+2, right? Really, this is just accounting for the delay slot. Okay. PC+2 means that we assume that the next instruction is always going to be unconditionally executed. That's why we actually calculate we add offset from is after this delay stop. That's what we're doing. Okay, so this is already baked into the assumption, the delay stop when we calculate the target address. All right, any more questions before we do the quiz? So the pause tool is over here, right? If not, let's do the quiz. We have a few more minutes, right?